In this video, I want to take a look again at exponential functions with complex numbers plugged into the exponent. And what do you do with them? But I'm going to do it this time from a point of view of sequences and series. When we were doing Picard's method, I think we ran across this first time, that supposedly e to the x is equal to 1 plus x squared over 2 plus x cubed over 3 factorial plus x squared over 4 factorial plus etc. I can show you the picture here of the red line is just the linear piece, so the 1 plus x. The orange curve is the quadratic 1 plus x squared over 2, then the cubic, and the fourth degree. The fourth degree, of course, would be 1 plus x squared over 2 plus x cubed over 3 factorial plus x to the fourth over 4 factorial. And yeah, this is the sequence of functions that is approaching the black curve in there, which is the e to the x. Okay. Now, it looks like I've still got a long way to go, and it's true. This is only, 4 terms out of infinitely many that would end up in the series. But let me offer this evidence that these two things are equal to each other. Consider the differential equation y prime equals y, with the initial condition that y of 0 is equal to 1. Now I know that e to the x satisfies that equation, because the derivative of e to the x is e to the x, so y prime is equal to y. And e to the 0 is 1. So e to the x is a solution to that first order differential equation that satisfies the initial condition. I happen to know a theorem that says any first order differential equation, given an initial condition, has one and only one solution. So there's only one function that works, and I know e to the x works. But take a look at this function of x over here on the right. If you plug a 0 in, all of this stuff turns into 0 and you just get a 1. So it satisfies the initial condition. But now let's take a look at its derivative. What's the derivative of this thing? Well, the derivative of a sum is the sum of the derivatives. And the derivative of 1 is 0. The derivative of x is 1. The derivative of x squared over 2 is x. The derivative of x cubed over 3 factorial, remember 3 factorial means 3 times 2 times 1. So you take the derivative, the 3 comes out in front and it cancels with 3 on the bottom, leaving just an x squared over 2. The derivative of x to the fourth over 4, of course 4 factorial is, this x to the fourth over 4 factorial. 4 factorial is 4 times 3 times 2 times 1. So take the derivative, you get 4x cubed, but a 4 cancels with a 4 on the bottom, leaving just an x cubed over 3 factorial. And in fact, the derivative of this power series is the same power series. It satisfies the differential equation y prime equals y, and it satisfies the initial condition y of 0 equals 1. But there can't be two different functions that satisfy that differential equation with that initial condition, so these two functions must be the same thing. So e to the x is equal to this thing. Okay. So now I'm going to use this to say, what is e to the ix? Well, essentially I'm just going to plug an ix in wherever I see an x. Right? I is, of course, the square root of minus 1. So plugging in ix here and there and there and there and so on. Now, I know, for instance, how to raise I to different powers. I squared is I times I, which is negative 1. And I cubed would be negative I. Actually, multiplying by I is an interesting thing, because remember, multiplying is just adding. You multiply the lengths, but you add the angles. And I is 1 up, so it's got a real component of 0, and it's got an imaginary component of 1. And so the angle with the positive x-axis is, positive real axis, is pi over 2. And so when I multiply that number by itself, it has length 1. You multiply with itself, so it's still going to have length 1. But the angle, pi over 2, gets added to pi over 2, and now you're over with an angle of pi. So you're over at negative 1. And then you multiply again to do I cubed, and you rotate another 90 degrees, another pi over 2, down to minus I. Multiply again, I to the fourth power, you'd be back at 1. I to the fifth, I to the sixth, minus 1. And you just keep going around that unit circle 1, I, minus 1, minus I, 1, I, minus. You just keep going around. Every time you multiply by I, you just keep rotating by another pi over 2. So these powers of I turn into, well, the I to the first power is I, the I squared is minus 1, I cubed is minus I to the fourth is 1, I to the fifth is I, minus 1, minus I, 1, and so on. So those I to a power just either is giving you a plus 1, a minus 1, a plus I, or a minus I. All right, to get this. Now what I'm going to do is I'm going to rearrange the terms. And I'm going to take all the terms that don't have i's in them and write them first. And then I'm going to take all the terms that do have i's in them and write them last. Now, I should point out that this is not always legal to do. That when we have a finite number of numbers being added together, that we have a commutative property. You can add them in any order you want. But when there's an infinite number, it isn't always the case that you can move them around. The theorem that we would get in a sequences and series class is that you can reorder them as long as you are within the interval of convergence for that series, okay, whatever that means. I will just tell you that the interval of convergence for this series is the whole real line, so we're good. We can do it. Right? You got to be careful because there's proofs out there of things like, oh, the sum of the positive integers is negative 1/12. Yeah, you watch those proofs and what they do is they do this thing. They move stuff around, but they do it while they're outside of the interval of convergence, and so who knows what the heck's going to happen. Yeah. Anyway, here's all the stuff without the i's. Here's the stuff with the i's. I'm going to factor the I out of those guys. I'm left with this. My claim is now, this sequence right here, this series, 1 minus I squared over 2 plus I cubed, I to the fourth over 4 factorial minus I to the sixth over 6 factorial. This is just all the even powers here with alternating plus or minus signs. And then over here, this is all the odds. This is equal to cosine x, and the stuff in parentheses is equal to sine x. Not immediately obvious, but here's some graphical evidence for you. I'll look at the cosine first. So here is the cosine curve. The red curve is the first two terms. It's the 1 minus x squared over 2. So that downward parabola shifted up 1. The orange curve has the fourth degree term in it. So what is it? 1 minus x squared over 2 plus x to the fourth over 4 factorial. And then the green one is the 6th degree, and the blue one is the 8th degree. And you can see how this is fitting closer and closer to that, that curve. And actually, we are pretty dang good, at least between minus pi over 2 and plus pi over 2 here. That blue curve fits pretty nicely through there. This is the power series for the cosine. Right? Notice they're all even powers and cosine is an even function. Yeah. And likewise, this one here has all the odd powers and sine is an odd function. Symmetric about the origin. Right? So here's for the sine. The red one is just the y equals x. The orange one is y equals x minus x cubed over 3 factorial. And then you've got the blue one, I think, is next, which would be x minus x cubed over 3 factorial plus x to the fifth over 5 factorial. No, that must be the green one. And then the blue one is with the 7th power thrown in. Okay. The sine as a power series. This one actually looks, well, not quite good enough from minus pi to plus pi, but dang, that looks really close there. I think one more term we would have it matching all the way along one cycle of the cosine, matching within, very small decimal places. Anyway, e to the ix looks just like cos x plus I sine x, okay, just as we wanted it in the last video. So then this brings us down to what happens if you have a combination of what is e to the alpha plus I beta, where alpha is a real number and beta is a real number, but then times I. So I got a real component and an imaginary component with the exponential. Well, the thing is, e to the alpha plus I beta is e to the alpha, which I can do. That's just e to a real power, then times e to the I beta. And here I have this formula now where I'm plugging beta in for x. And so e to the alpha plus I beta is going to turn into e to the alpha times the quantity cos beta plus I sine beta. And we will use this now to find solutions to those differential equations when the roots to my characteristic equation are complex numbers. So there you go.